Okay, let's look at more interesting saddle points because that matrix was boring. So I want you to find the general solution. I know that part of that F is blue, I'm sorry. Find the general solution of the differential equation dy dt equals b times y, where b is the coefficient matrix 8, negative 11, 6, negative 9. And I'm going to let you do this. So pause the video for extra practice. If you're feeling like 3.2 is super easy, you're great at finding eigenvectors and eigenvalues and general solutions, you could skip. But please pause the video and do it by hand if you want some practice. And what you should get is the general solution of, I lost my place in my notes, k1 e to the negative 3t times the eigenvector 1, 1 plus k2 e to the 2t times the eigenvector 11, 6. And you might have different eigenvectors than me, right? Maybe you have the eigenvector 22, 12. That's fine. Maybe you have the eigenvector 5.53. That's fine, right? Because it's any multiple. So k times 11, 6 is the same as k times 22, 12. If k could be any real number, they're equivalent. All right. So as long as it looks something like this, then you should be pretty good. And we're going to do some qualitative analysis. We're going to do something also a little interesting here. And specifically, I'm going to, and I should have created this grid before, I want to actually plot this by hand. What is this straight? What does our phase portrait look like if we plot it by hand? Actually, we're going to need smaller grids, huh? 11 kind of 6. 11, 6 is kind of a big number, huh? All right, so here is our plane. We're going to label our axes. It's very important. Always have to label your axes in really any math class, but especially differential equations. This is going to be our x-axis. This is going to be our y-axis. Remember, there's no t in our phase portraits, just like there was no t in our phase lines, right? These are autonomous differential equations. We're not really going to be worrying about, we're not going to be graphing t really. Although again, in some of our phase plotters, t is like on that phase plotter that we used earlier, right? The time components kind of showed with color, which is pretty cool. But anyway, we know that there's a straight line solution in the direction of 1, 1. So a straight line solution across this diagonal line. Right? This is a straight line solution. This is the line y equals x. And specifically, lambda is negative there. So we know that any solution on this line is going towards our equilibrium solution at 0, 0. And there's another straight line solution that's a little bit more interesting. 11, 6. I'm going to do 5.5, 3. 1, 2, 3, 4, 5.5. 1, 2, 3. That's a little easier to count. 1, 2, 3, 4, 5.5. 1, 2, 3. And hopefully, if I graphed right, I can draw a line through all of this. And we get another straight line solution. And specifically, we know that with this one, right, it has a positive lambda. Positive lambda means along this straight line, we're getting pushed away from the equilibrium point. And as soon as we have this, we essentially can make our own phase portrait. We know, we didn't cover it in chapter 2, but I kind of said that if we have a nice enough differential equation, we have a system of differential equations, then we have uniqueness in existence of solutions. And uniqueness for systems of equations is pretty similar to uniqueness of single equations, right? Are different. As long as we have autonomous systems, our solutions are not going to cross. If they're non-autonomous, then we have a sort of third dimension, and they can kind of cross from a certain point of view. But anyway, for autonomous systems, they're not going to cross. So we know our solutions are going to kind of be like propelling one way, and then going the other, right? The whole point of a saddle point, and this is saddle, right? One's positive, one's negative for the eigenvalues, is that we're getting propelled along one and away from the other. So we really have solutions that kind of look like this. All right, no solution's ever going to hit the origin. That's a weird thing about equilibria. Even sources, which are going to go towards them, will never actually touch. They'll get exponentially close. Anyway, yeah, so that's our phase portrait. We can do it by hand now. That's pretty cool. It would be so tedious to do the vector field by hand, but we can get a pretty good idea about the behavior of solutions just using these straight line solutions and what we know about the eigenvalues and stability. And again, this is a saddle point. It looks a little different than this saddle point, but it's the same sort of behavior, right? Just what happens if you took these straight line solutions, squished them together, then all the other solutions kind of get squished together as well. Okay, and let's also plot this with a nicer plotter. Okay, so this is the system. Our matrix is 8, -11. Oh, I can press tab. And then 6, -9. And we can see, wait, actually that does not look like what I drew. I forgot a negative here. I was like, this is supposed to look like what I drew. Okay, that looks a lot better, right? That looks pretty similar to what I drew. We can see the eigenvectors, the straight line solutions, the arrows. This plotter is kind of missing the solutions over here. I'm not honestly as familiar with the plotters here. We can see our eigenvalues of -3 and +2, just like we said. It has slightly different eigenvectors, but again, any scaling of our eigenvectors are the same. Our first eigenvector was 1, 1. Their first eigenvector was -6, -6. It's the same eigenvector. Okay. If we really wanted to see it, maybe a nicer phase plotter, we could use that older one. I like this one because it shows the eigenvectors really easily. I don't think there's a place to show eigenvectors here. But yeah, this is just, 8 times x minus 11 times y. This is 6 times x minus 9 times y. And again, we can just see exactly what's happening over here. We can plot a bunch of solutions. Oh, look. Yeah, you can see that, right? You can get those like middle solutions that we were kind of missing in the other one. These ones that kind of look hyperbolic. All right. So we can see that, yeah, we had a pretty good guess for our phase portrait. Nice job, us. All right. So the next thing I want to talk about, the last thing on saddle points before we get into sinks, we'll talk about sinks in the next video. The last thing I want to do for saddle points is look at an initial value problem. We haven't really done those yet for systems, at least in 3.2. Consider the initial value problem. That's the same ODE. I'm going to be a little lazy. So, right, it's still dy dt is b times y, same b. And our initial condition is y naught equals 0, -5. So we could use this initial condition to find what K1 and K2 have to be. Or we could do qualitative analysis, like use our qualitative analysis to say exactly what's going to happen here. So let's do both. All right, if we're starting at 0, 5, what do you think our solution is going to do? Well, that's starting at 0, 5, 1, 2, 3, 4, 5. That's starting here. What do you think the solution is going to do? X is going off to infinity. Y is going off to -infinity. Or X, they're both going off to -infinity, right? We're both shooting down that way. That's what we, wait a minute. That doesn't sound right. I think it's more like this. So maybe the qualitative analysis is not perfect here. Wait, actually, I don't know. No, I think I was right. I think they're both going to -infinity. Well, here's what happens when you talk too fast. So they should go down. I think they both go down to negative infinity. There's always some, like, jokes aside, right? There's always some ambiguity in qualitative analysis. We definitely know what direction things are moving. The end behavior is not super clear, but yeah, I'm almost positive we're going to go down and kind of approach this line. But let's see. Okay. If this is the case, you could plug things in and find your K1 and your K2. Again, recommend look at the general solution. We'll do this together. Why not, right? So remember, y1 of t was K1 e to the negative 3t times 1, 1 plus K2 e to the 2t times 11, 6. And remember, we can always rewrite this if we want. This is how we often rewrite it, but you can also rewrite this as K1 e to the negative 3t times 1 plus 11 times K2 e to the 2t as the x coordinate, right? And then the y coordinate is K1 e to the negative 3t plus 6 times K2 e to the 2t. So these are equivalent ways of writing it. The top one really shows you what x of t is and what y of t is a little quicker. Because we know the initial value is that x is initially 0, y is initially negative 5. What are our constants? I'm going to regret doing this. When t is equal to 0, we get K1 plus 11 K2. That needs to equal 0. And when t equals 0, the y equation becomes K1 plus 6K2 needs to equal negative 5. We have a systems of equations. We can actually solve this pretty quickly, right? With elimination. If you subtract these two equations, what you're going to get is just 5K2 equals 5. So K2 is just 5. No, 1. And if K2 is 1, K1 has to be negative 11. All right, good. And so we do have our particular solution for this initial condition. It's just going to be K1, which we said was negative 11. And actually, I'm going to write it in this vector form. K1 e to the negative 3t plus 11 times K2, which is 1, e to the 2t. And then similarly, write K1 negative 11 e to the negative 3t plus 6 times K2 e to the 2t. Check my work to make sure that I didn't make a silly mistake. Negative 11 e to the 3t, negative 3t, plus, yeah, I wrote them down in different order on the other one. That's interesting. Okay, that is right. That's our particular solution. Now we can answer the question. Does it asymptote to 0? Does it asymptote to this straight line solution? My guess is it goes to the straight line solution, but let's see. As t goes to infinity, what happens to this solution? Well, as t goes to infinity, y of t, as t goes to infinity, this goes to 0, right? So as t goes to infinity, y of t approaches, like, essentially becomes this function, no? As t goes to infinity, y of t essentially becomes this function. That is our straight line solution. So I was right the first time and the last time, not the second time. This is the correct picture. It is going to approach this red line. And specifically, it's going to behave this way. Wait a minute. This goes to positive infinity as time goes on. Am I off by a sign? Did I make a sign error or a arrows error? It's an excellent question. and you can give me the answer to that, or I will make a comment above the video or below the video. But that's pretty much what we have right here. We can analyze this as well. No, I'm gonna do it right now. It shouldn't take long. I can always crop this out. So, right, as t goes to infinity, the x coordinate's going to infinity for 0. Oh, it's 0, -5. I see. So I had the wrong initial condition in my head, right? It's not 0, 5 up here. Our initial condition was 0, -5. So that was a mistake from a long time ago, actually. But yeah, they're going up here. And again, it's approaching same line, but yeah, they're both going to infinity. Whew. Sorry about giving you so much of a video where I was trying the wrong vector. That makes me feel better though. All right, so that's the long-term behavior, right? It's approaching that. Is that a coincidence? Is it a coincidence that as time goes on, for this saddle point, we're approaching one of our straight line solutions? Think about it. I will answer the question before the end of this section, but not before the end of this video, because the end of the video is right now. That's it. Let me know if you have any questions, and have a good rest of your day. The next video, we'll talk about sinks.